So today what we're going to do is take a look a little bit closer at how the Gaussian model, the logistic growth model, and also the logarithmic model is used. Okay? So we'll look at a couple of applications of each of these and hopefully even just give you some time to practice with them in class and then finish up outside of class. But looking first of all at the Gaussian model, we said the Gaussian model is also known as what? What is it?
The bell curve?
The bell curve, yeah, the normal curve. A bell-shaped curve. I don't know where that's not going. Alright, so for example, here we have 4e to the negative x squared. Okay? Are you collecting?
Have you got everybody?
Yep.
Oh no, it's not review. Besides, I don't review.
Aha! Trying to get away with it.
Oh, I didn't even notice. You
Yeah,
had the
yeah.
shorts.
So I have a student next door who I walked up to him and I said, "Where's your dress down money?" And he's wearing his NB baseball shirt. He goes, "I'm in uniform because normally Friday's is Spirit."
Oh, I didn't even
I
think
said,
of that.
Technically you're
Yeah.
right. Are you wearing a Spirit shirt?
Yeah, but my short also.
Ah, you ruined it.
No. What is it, $1.50 then?
It's to charity, so like.
Yeah.
So it's worth it. Well worth it. Thanks.
Alright. So we're looking at the Gaussian model, and the key thing to see this, okay, if you're looking at one of the models and you're not sure which equation we're dealing with, okay, the key thing that makes this the Gaussian model is that the x in the exponent is squared. Okay? That's what makes it, rather than like the exponential here, go up and keep going up, that's what makes it come back down. Okay, is that squared aspect of it. Okay? So we have this Gaussian model, in this case 4e to the negative x squared. One thing when you're graphing it though, if you are dealing with a case where you know you're dealing with percentiles, okay, or probabilities even. This isn't the only application. Like for example, this one, notice it goes all the way up to 4. Okay, but if you're dealing with a case like this, or we have SAT scores, the highest it's going to go ever in this case would be 1. And that's if everything were exactly on the mean. Okay, it would go all the way up to 1. It would just be a point, actually. Alright, but that wouldn't even be a normal distribution. That would just be a constant there. But that's why sometimes this is hard to actually see when you graph it on your calculator. Because notice in this case, I'm looking at x values going from 200 all the way to 800. So I made my window go from 0 to 900, okay? But the y values at the highest are going to be at 1. And in this case, we actually had to zoom in even closer. Notice, this is just going to 4 1/1000ths in order to actually see it, all right? So this is where maybe using box zoom would be helpful, because when you go to graph it, it's really not going to be easy to find if you're not thinking about the function itself. Okay, so here we have in 2005 the SAT math scores for college-bound seniors roughly followed a normal distribution, and there was our distribution. Okay. So 0.0035 e to the negative parentheses x minus 520 squared divided by 26,450. Okay, now let me point out a couple of things here that will help you as you're trying to graph this, because if I just hit graph right here without thinking, okay, I don't see anything. Alright, but okay, then I say, oh wait, x had to go from 200 to 800, so I'm gonna go from 0 up to 900 just to make sure I get everything. And now I hit graph and I still can't see a thing. Alright, but remember what we've seen with our other exponential models. This value out in front was usually our starting amount. Okay, now it's not technically the starting amount or the amount when x is 0 in this case, but it does help us see, if we think in terms of vertical stretch and shrink, this thing is going to be shrunk pretty small. Okay, and what you might even do is try just setting it so that your window, for one thing, this isn't going below 0, so I'll start at 0, and then I'm just going to go up to a 0.0035 just to try it at first. Okay? And you can see it goes right up to the top there. Okay, so this value right here is going to be the highest it goes. Okay? Now, all of that to say, we've got to, we have to be able to understand the graph in order to make our calculator useful. Alright, the calculator can do all kinds of stuff, but if we can't actually even find where it is on the graph, it's not going to help us at all. Alright, now, from what you guys know about the bell curve, where would the estimate of the average SAT score be?
When y equals 0.0035.
Okay, which is where on the graph?
Oh, it says it.
520.
What?
520.
At 520, where on the graph is it?
Very top.
The peak, the very top. Okay, if you remember what we looked at when we studied the normal curve, the very center, the peak, was the mean. Okay? Now, you can also see the mean right here. 520 is the mean. When you have x minus something, because normally a Gaussian function is centered right on the y-axis. It's symmetrical about the y-axis. But this shifts it over to where the mean is. Okay? So, again, understanding a little bit about these functions helps us, about the equations of these functions, helps us be able to find different values easily and also be able to see the graph pretty easily. Okay? So that's our Gaussian model, right? Named after Carl Friedrich Gauss, who is the one that kind of came up with the whole thing. So, along with a bunch of other stuff, he was pretty brilliant. Another one here is the logistic model. We talked about this a little bit. It's also known as a sigmoidal curve. Okay? Because it kind of looks like an S. Alright, but the model shows a situation where something starts to grow exponentially, but then that growth is slowed by some other influence. We talked yesterday briefly about this, where you have a certain capacity that can fit in a stadium, and you're looking at the people coming into the stadium. Alright, you also have the start time for the game that's going to affect when people are coming in. Alright, so the closer you get to the start time for the game, the more of an influx of people, and then once the game is started, and once the stadium fills up, or is starting to fill up, there's fewer and fewer people who are showing up, so the increase slows down. Okay? Another case here is the spread of a virus, and I actually want to do this problem here. You guys are preparing for college, so here's something to consider, but don't think about too much, or else it might freak you out. On a college campus of 5,000 students, one student returns from vacation with a contagious flu virus. The spread of the virus is modeled by this logistic function. The key to recognizing this as a logistic is that you have a 1 plus something e to the t power in the denominator. Okay? Now it says y is the total number of students who are infected after t days. And if enough people get sick, the college will actually cancel classes. Alright? College will cancel classes when 40% or more of the students are infected. There was one time when I was in school where we actually had classes canceled for a day because there was so many people sick. But that only happened once. And that was back, I don't know if you remember, that was back, well, I'm dating myself here, this would be about 2005. No, not 2005. I graduated in 2003. It would have been like 2002 or so. There was a big outbreak of like whooping cough. And that went like nationwide almost. But that's when they shut down classes for a day.
Was it a good day?
I wasn't sick, so yeah, it was good for me. But, so here we have part A. How many students are infected after 5 days? What do we have to do here? Yeah, this is just plug and chug. Plug 5 in for t, figure out what it equals, okay? So let's go ahead and do that. All right, grab your calculators. Grab your calculators and let's figure that out, okay? Be careful with parentheses.
No, solo 5,021. Es que hace 5,25 es 500.
Alright, so how many people are sick now?
54. Oh, wait, no.
981.
I think you guys forgot to put parentheses around your denominator. You should have parentheses around the 1 plus 4999.
54.
You got 54? Okay. Yeah, there we go. 54. If we plug in 5, there are 54 people sick. That's kind of disconcerting. One person gets sick, and after 5 days, if they're really contagious, we could have 54 people sick. Alright? So, okay. So part A, we've got 54 people sick. Now question, if the school is going to cancel classes once 40% of the people are sick, how many people do we need to get sick?
2,000.
Okay, 2,000 out of the 500, alright? So,
Plug nothing for y.
yeah, that's it. We've got for B, 40% is 2,000 students. Okay? And we can solve this one a couple of different ways. We can actually do 2,000 equals 5,000 over 1 plus 4999 e to the negative 0.8t.
Isn't there a property where you can switch this here?
Where, what, the denominator with the 2,000? Yeah, basically you're multiplying both sides by this, and then you're dividing both sides by 2,000. So yeah, you could do that. 1 plus 4999 e to the negative 0.8t equals 5,000 over 2,000, so that's 2.5. Okay?
Subtract one from each
We
one.
subtract 1, so we've got now a 1.5.
Divide by 4.
And what? There we go. We've got to divide by 49.99. Okay? So, divide by 4,999. And once we get to that point, let's get caught up here with our calculation. We have 1.5 divided by 49.99. And then what do we have to do with that?
Store it. Or take the natural log of it.
There we go. Yeah. We're going to take the natural log now of that, and that will give us a negative 0.8t. Okay? So, hit natural log of that previous answer. As long as it's on the previous line, you can hit second negative for the previous answer.
Negative
And
8.1115.
divide.
And then divide by
Yeah.
negative.
Good, now we're dividing by a negative 0.8. 10.13 days. Okay? So this was a negative 8.11. Okay, so t is 10.1 days. Alright, or 10 days. Okay? So probably on the 11th day we're going to end up with a day off. Okay? Now, the reason why this is kind of nice to use as a model, as opposed to a model where we're just looking at exponential growth, is the exponential growth model would assume that nobody's taking medicine or trying to not cough on other people, or, you know, people aren't being careful, people are still going to class sick. That's what the exponential model would do. And obviously, how would that differ? If people really weren't trying to be careful and keep their sickness to themselves, what's going to happen?
Maybe it'd be higher.
Yeah, the rate would be a lot higher. Okay, this thing would spread a lot faster. But this logistic model takes into account the fact that, you know what, after a couple of days, the first people who are sick are actually getting better now, hopefully.
And people will react to it and try and solve it the way it had not.
Exactly, yeah. People who aren't sick are probably popping vitamin C a lot and trying to stay away from the sick people, and people who are sick aren't going to classes anymore. So there are a lot of factors that go into that, into why this ends up leveling off. Okay, yes?
Where would the horizontal asymptote be?
The horizontal asymptote actually would be when we reach capacity, 5,000 students. Okay, if we were to look at this on a graph, 5,000 divided by parentheses 1 plus 4,999 e to the negative 0.8x. Alright, I need my window to be set going from 0 to, let's say, 15, well, let's say we go all the way to 20 days. And my y min, I'm going to have go from 0 up to 5,000 students. Okay, and actually, you know, let's stretch this out for a month. So here's 30 days. Now when I graph it, you can kind of see we're reaching capacity. Alright? So at this rate, everyone eventually will get sick. Okay? But but that's where, to avoid that happening, we need to take some further interventions, and that's why they would shut down classes. Okay, because once we've hit 2,000, all right,
So you could like restrict the domain and then have like another equation.
yeah, you could do some kind of a piecewise here. But there's 10.1, we're at 1962. Okay, so let me see, 10.11, 1971. All right,
1.34.
so 10.34.
No,
No, 1.34.
Oh, 134. There we go. I'm in 1994. We're getting closer and closer to 2000. All right, so they've evidently realized, hey, once we get this point, in order to avoid it to keep skyrocketing, we need to take an intervention. We need to cut it off and cancel classes so everyone can stay home, stay away from each other, and get better. Okay. So, kind of an interesting study there. I'm not sure what it is here, but I know, like, for the school I used to teach at up in Ohio, if we had 30% of the kids sick, I think it was 30%, then they would cancel school. So, which for us was only like 42 kids. So, all right. So our last model is the logarithmic model. Okay. Now this is a function that we're familiar with already because we've dealt with the parent function a little bit. Okay. But I wanted to see a case where the logarithmic model is used, and one good example is in the Richter scale. Okay. The Richter scale is a way of measuring the magnitude of an earthquake based on its intensity, okay? Its intensity, I. And the thing that maybe you don't realize is that because this is a logarithmic scale, okay, every tenth on the Richter scale represents an intensity that is 10 times greater than the previous tenth. Okay? So a 5.0 is 10 times more powerful as a 4.9 earthquake. Alright? A 5.0 is 100 times more intense than a 4.0. Think about that. That's pretty incredible. So that's why sometimes you can hear in the news, oh, there was this earthquake that was like, 3.5, and not a whole lot happened, and then there was another one that was just 4.0, and there was a lot of destruction. Well, that's because it was 50 times more powerful. Okay? So pretty impressive. What we have here, though, we have a case in 2001, the coast of Peru experienced an earthquake that measured 8.4 on the Richter scale. And in 2003, Colima, Mexico experienced an earthquake that measured 7.6. Okay? So find the intensity of each earthquake and compare the two intensities. Well, the intensity is measured using this model. Okay? The magnitude, R, for Peru was 8.4. That equals the log base 10 of whatever the intensity was over I sub naught. Okay? Now, I sub naught just stays I sub naught, and this is why we have to compare two of them together. Because this intensity here, alright, how would I solve for I?
Isolating it?
Yeah. How?
Log 10i minus log 10i 0i.
We could do that, split this into two logs. There's a little simpler way though here.
You would say 10 to the power of both sides.
Okay, good. Let's write this as an exponential and make this 10 to the 8.4 power equal to I over I sub naught. Right? Okay? So now we know that the intensity level in Peru was whatever I sub naught is times 10 to the 8.4. Okay? Now in Mexico, where we had a 7.6, 7.6 equals the log of I over I sub naught. So use the same process. 10 to the 7.6 power is I over I sub naught. Okay. I equals I sub naught times 10 to the 7.6. Okay? Now, how would we compare these if we're trying to compare them?
Plug in a value for I sub naught. And keep it the same for both.
Yeah. We could, but I mean, what would you do with that then? I mean, when we're talking about a mathematical comparison, what are we talking about?
Ratio.
A ratio, okay? A ratio. So, if we're going to compare Peru to Mexico, okay, we would do I sub naught times 10 to the 8.4 over I sub naught times 10 to the 7.6. And that's going to give us
I over I. 10 to the
8.4 minus 7.6.
10 to the 0.8 power. Okay? 10 to the 0.8 power. Alright? So the comparison of the intensity as a ratio would be 10 to the 0.8, which, what does that equal? What's 10 to the 0.8?
6.31.
Okay? Oh, I misspoke. It's not every tenth. Every unit on the Richter scale is 10 times more intense. Not,
Like 1, 2, 3, 4, not 0.1.
yeah, those are 10. Yeah, sorry. Yeah, every unit, not every tenth of a unit, is 10 times more intense. So a 4 would be 10 times more intense than a 3. Okay, alright, it was one too many powers of 10 there. So this one that was 8.4 is 6.3 times as intense as the 7.6 degree earthquake in Mexico. Alright? So that's how you can compare them. And this isn't the only thing that's measured this way. The I sub naught is basically what's the intensity, so to speak, if there's no earthquake at all. And there's always little rumblings going on under the surface, okay? So that's kind of our baseline, and that's what they're accounting for here. So compared to normal, then we have these intense shock waves going through, and they measure those, okay? They do the same thing actually with decibel levels. Decibel levels, they compare it to silence, the intensity level of silence, basically, or just white noise that you have in the environment. And then they do comparisons. The interesting thing is there, if you had, one stereo playing at a certain volume, and then you put a second one right next to it, it actually doesn't double the decibel level, it doubles the intensity, but doubling the intensity only increases the decibel level about 3 decibels. Okay? Otherwise, if everybody started talking all at once, it would be unbearable, you know. So kind of an interesting thing here. All right, now for your practice, I gave you some of these. I gave you the vocabulary check because I want you to be familiar with the vocabulary. Don't do that now. Go home, do that by yourself, okay? And also matching models with the graphs of them. I want you to take the time to do that on your own, okay? But right now, take some time and skip to number 36. And you can use the last 10 to 15 minutes of class here to practice working with some of these. And pay close attention to what the variables are representing, because some of these are just plug a value into the formula and evaluate, okay? Don't overcomplicate those. Others, however, you have to set it equal to something, okay? And don't forget, too, that another valid way of solving the equations is by graphing it, and then you can put the value you want in as the horizontal line, and then what do we do?
Find the intersection.
Yeah, find that intersection point. Okay, remember we did that with the problems that we did on Tuesday. There were some that you couldn't solve with, manually. So you had to, if we want to know when this equals 2000, we put y2 as 2000 and then intersect those two. So that's another valid way of using technology to solve some of these equations, okay? But at least try it algebraically, see how well you do, okay? All right, you can start working on those now.